So in this video, we're going to look at some situations where you're going to find resultant vectors, some applications where the goal is to find resultant vectors. Remember, a resultant vector just comes from adding two vectors together. So let's first, before we look at actual examples with different values, let's think about this situation of, like, let's say that you and your friends are at a river and you're on one side of the river over here and your friends are over here. And the current is going in this direction at a certain velocity, right? Speed and direction. So the current is traveling in that direction at a certain speed. You have the goal of swimming from one side of the river over to your friends. So you get in the water and you start swimming as hard as you can to get over there to make up for the current. So you're trying to swim upstream. Your goal is to swim in a direct line to your friends. So you set out at like an angle that would make you swim towards your friends, and you're swimming at a certain velocity, right? Like you're putting a certain amount of work in. However, you're swimming and you're kicking your legs, and the current is then also moving you. So the velocity of the current is also working against you. So it's going to make it very difficult to actually swim in the straight line over to your friends. Like if you're head down, just kicking and paddling or using your arms, like you may end up maybe more like downstream over here, depending on what the velocity of the current is. So in that case, that would be like the actual vector that would, like, your actual velocity. So there's the velocity that you're trying to swim out. Then you have the velocity of the current, and then the actual velocity, so the actual speed and direction that you end up traveling in, it is a third vector quantity. So we're going to look at a few examples of where we're going to calculate a resultant vector. The first two examples are going to have to do with velocity. So this first example says a boat's speedometer reads 25 miles per hour, which is relative to the water, and sets course due east 90 degrees from due, which is 90 degrees from due north. If the river is moving 10 miles per hour due north, what is the resultant or the actual velocity of the boat? So I'm going to draw a two-dimensional plane. However, instead of labeling as X and Y, I'm going to label north, south, west, east. But I'm going to draw each of these vectors, so each directed line segment that represents these different vector quantities, I'm going to draw them in standard position. So the first vector quantity that we're given is the velocity of the boat. So I'm going to call that vector B to represent the velocity of the boat, which is 25 miles per hour and sets a course due east. Okay, well, if it's a vector, the boat is driving directly east and its speed is 25 miles per hour, the vector that would represent that would terminate at the position 25, 0. Right? So it would terminate at the point 25, 0. Because the magnitude is 25 miles per hour. Okay, the next vector quantity will be the velocity of the river. So call that, how about vector R? And the river is moving 10 miles per hour due north. Due north, so pointing up. So that point where it terminates would be 0, 10. So in component form, that would be 0, 10, like so, with the pointy brackets. So the resultant velocity is going to be the velocity at which the boat is actually traveling. And we can come up with that velocity just by adding those two vectors together. So our resultant velocity, which we can call, how about let's just call it V, would be vector B plus vector R. So we can think about adding those two vectors together, which would just be, I'm going to write out all the steps here. It would be 25 plus 0, comma 0 plus 10. So 25, comma 10. So this makes sense for parallelogram method, right? This terminating point would be 25, the resultant vector would be 25, comma 10. However, knowing the position vector is great. The vector that represents the actual velocity, right? This represents actual velocity. But we want to be able to describe our answer. Like we want to be able to describe the magnitude and the direction, the actual velocity of the boat. So we need the magnitude. I'm going to give myself an extra sheet here, extra page. So the magnitude of vector V, the actual velocity, right, would be the square root of 25 squared plus 10 squared. If we pop that into our calculator, it ends up being approximately 26.926 miles per hour, or let's just say approximately 27 miles per hour. For angle, let's think about theta. We're in quadrant 1, so theta is going to be accurate for the direction angle. So inverse tan of 10 over 25 ends up being approximately, I'm in degree mode because I want to angle in degree. So inverse tan of 10 over 25 would be approximately 21.801 degrees, or I'm gonna round that to approximately 22 degrees. Now, we want to give a little bit more, like just saying 27 miles per hour, 22 degrees, what, right? For describing the direction. So why don't we say, since this is the angle that we just came up with for theta, why don't we say 22 degrees north of east? So we can say the actual velocity of the boat is 27 miles per hour, 22 degrees north of east. I'm not going to get too in the weeds on the direction. Just make sure that the words you're using to describe the angle that you use makes sense. Like if you had found, for some reason, like this angle. You could have said that that angle was east of north, whatever that angle is, east of north. So just make sure that it makes sense. Okay, so another boat problem. So a speedboat traveling 30 miles per hour has a compass heading of 100 degrees east of north. 100 degrees east of north, okay. The current velocity has a magnitude of 15 miles per hour and its heading is 22 degrees east of north. Find the resultant or the actual velocity of the boat. So let's, again, try and represent these vectors by picture. So north, south, west, east. And to represent these vectors, we're going to need to come up with the horizontal and vertical components using that A comma B is equal to the magnitude of the vector times cosine theta, comma the magnitude of the vector times sine theta. Okay, so the vector that represents the velocity of the speedboat that the speedboat is trying to drive at is 30 miles per hour at a compass heading of 100 degrees east of north. So 100 degrees east of north would be about there. So it would be coterminal. We would think of that angle as being about negative 10 degrees. So this angle is actually 350 degrees. And it has a magnitude of 30 miles per hour. So in component form, that would be 30 cosine. I'm using 350 degrees for the direction angle because that's the angle that's in standard position. 30 sine of 350 degrees. And I can't simplify that further because 350 degrees is not on the unit circle. The current's velocity has a magnitude of 15 miles per hour and is heading 22 degrees east of north. So the current, I'll use green for 22 degrees east of north. So let's say that is our current vector. It's a magnitude of 15 miles per hour. So 15 cosine of the direction angle, 90 minus 22 would be 68 degrees, right? Because I want the angle in standard position. I don't want to use the 22 degrees. I want the angle in standard position. So 68 degrees, comma 15 sine of 68 degrees. And then we want to find the resultant vector, which we can find from adding those two vectors together. So I'm going to give myself a little bit more room. Okay, so the resultant vector, I'll use orange, I'm going to call it vector V, which will represent the actual velocity. We can find that vector in component form from adding the two horizontal vectors, the two horizontal components together. So doing 15 cosine of 68 degrees plus 30 cosine of 350 degrees. And then the vertical component will be 15 sine of 68 degrees plus 30 sine of 350 degrees. So that will represent the resultant vector, right? That's A, that's B. You could store those values in your calculator if you would like, because the magnitude of vector V will be the square root of A squared plus B squared. So if you store those into your calculator, then you don't have to write all of that out. Or I'm assigning them as A and B. If you want to write it all out, you can. Here, I'll show it all written out too. So the square root, you can type this whole thing into your calculator, of 15, or since I'm in Notability, let me just copy and paste it. So this squared plus B squared. Okay, and that ends up being approximately 36 miles per hour, rounding up. Okay, theta is going to be inverse tan, which I'm pretty sure this resultant vector has a direction angle in quadrant 1, like the angle that we're going to get is it's inverse tan of a positive ratio. I'm pretty sure it's an angle in quadrant 1, but let's double check. So you could put in B over A if you've assigned those values, or you can write this all in. So B over A. Okay, and that ends up being approximately 14 degrees. So this ends up being, that would make sense for the picture. So this ends up being approximately 14 degrees. You could say north of east. The magnitude of 36 miles per hour. So we can say that the actual velocity of the speedboat is approximately 36 miles per hour, 14 degrees north of east. Or something that makes sense. Could have also said about 76 degrees east of north. Okay, and then resultant forces. We've given a picture. A barge runs aground outside the channel. A single tugboat cannot generate enough force to pull the barge off of the sandbar. A second tugboat comes to assist. The following diagrams illustrate the force vectors F1 and F2 from the tugboats. What is the resultant force vector of the two tugboats? So how much force is actually pulling on the barge? Okay, so I'm going to adjust this picture and give myself another page. And then I'm going to adjust this picture so that it's drawn in the XY plane. So I'm going to draw the second force as being on the positive x-axis, so F2. And then it would be represented in component form as 18,000, 0. And then F1 would have a direction angle of 20 degrees. And I know the magnitude of that force and also the direction angle. So F1 could be represented as 15,000 cosine of 20 degrees, comma, 15,000 sine of 20 degrees. Okay, this will allow me to think about just adding the two components together to find the resultant force. So the resultant force, which I can call, I'll call it F3, would be 15,000 cosine of 20 degrees plus 18,000, comma, 15,000 times sine of 20 degrees. So just adding the horizontal and the vertical components together. The magnitude of the force, so this would be, right, that'll kind of end up being F3. The magnitude of that force, so the actual force, the resultant force, will be the horizontal component squared plus the vertical component squared, the square root of that. Which ends up being approximately 32,503 pounds. The direction angle, which since we're in quadrant 1, this will be the actual direction angle, will be inverse tan of the vertical component divided by the horizontal component. And we get approximately 9 degrees. So this angle would be approximately 9 degrees. So we can say that the resulting force on the barge is approximately 32,503 pounds at an angle of approximately 9 degrees from the tugboat line pulling a force of 18,000 pounds or something in an angle, some sort of direction. So whether it's off of the first force or the second force, giving some sort of interpretation. Okay, so all three of these word problems were examples of finding a resultant vector. So adding two vectors with given, which you know those vectors from the given information, adding them together in order to find the resultant vector and identifying the magnitude and direction of that vector to interpret your answer.